Lesson 7.4, day 2, we're going to have more transforms of actually integrals today. Let's just say that you have two functions. However, they must both be piecewise functions. They must also be continuous piecewise functions from 0 to infinity. A convolution, and this is going to look a little different. It's really just this asterisk. When you see two piecewise functions, they're continuous. If you take the convolution of them, f convoluted with g, that plain and simply is by definition the integral from 0 to x of f of t times g of x minus t dt. So we just simply work out this integral. It's by definition. Of course, we're very accustomed to also seeing our functions written with respect to t, and that's what we're seeing over here just as well. What if our argument was a t instead of x? Well, if that were the case, you can see that, now we'd integrate from 0 to t, but as is the custom, we'll use the Greek letter tau instead of using a little t like we did previously. So that would be the integral from 0 to t, f of tau, times g of t minus tau, and we would integrate with respect to tau. So let's take a look at an example, example 1, and it will say find the convolution of e to the 3x and e to the 2x. So I'll have e to the 3x convoluted by e to the 2x. And you might wonder, are these really piecewise functions? You could define them to be piecewise. There's certainly, you could just have one assignment if you'd like, and they're certainly both continuous. But as we follow these guidelines right up here, we could say we're going to integrate with bounds from 0 to x. And here's our f. We'll have f of t, so that'll be e to the 3t. And then we're going to multiply to that g of x minus t. Well, instead of having an x, we're going to have x minus t right in here. And then, of course, we're going to integrate with respect to t. Well, as we're breaking this integral down, we'll have our e to the 3t as we distribute. We'll have e to the 2x minus 2t. And, of course, right now we're just going to really use our exponent properties. We're going to add our powers together. I'm going to continue up over here. We're going to integrate from 0 to x. When I add 3t plus 2x minus 2t, we will have really just a 2x, then plus a 1t, or just a plus t itself. What am I doing? I'm just adding these powers. I'm really using this property of x to the a times x to the b is x to the a plus b. And 3t plus negative 2t is 1t. So now what? We're going to take an antiderivative with respect to t. We don't have to reverse a chain rule, so to speak. We'll just have e to the 2x plus t. And then we're going to double check by taking a quick derivative. You can see we're right back to our integral. But now we're going to apply that fundamental theorem. Plug in an x, you'd have 2x plus x, that's e to the 3x. Minus, when I plug in a 0 with respect to t, you can see we're just going to have e to the 2x. Here is our convolution. Plain and simply, we'll have e to the 3x minus e to the 2x. Likewise, if we find the convolution for example 2, x and x squared, well, let's see what we've got here. We'll have x convoluted with x squared. Looking at the top here, we're going to say we're going to integrate from 0 to x. We'll have f of t. Well, f of t is simply a t. And then we're going to have g of x minus t. Well, I think you can see already that's going to be x minus t quantity squared. And of course, we're integrating with respect to t. As we continue on, let's expand this thing here. We'll get x squared minus a 2xt plus t squared. And then we're going to distribute a t in all the way through here. So we'll have the integral from 0 to x, and we'll have really a tx squared minus a 2xt squared plus t to the third. And there's a dt. And guys, as we take our antiderivative, again, with respect to t, we will have for our first term t squared x squared all over a 2 minus, well, now we'll bump this up to t to the third. We'll have to divide by 3. And then over here we'll have t to the fourth all over 4. But with the fundamental theorem, we're going to be applying this from x to 0. So as we plug in our x, we'll have x squared times x squared. That's x to the fourth all over a 2. Plugging in x right here, we'll have x to the third times x. That's x to the fourth. That's 2. X to the fourth all over a 3. Here we'll have x. And you can see as we continue, we're going to plug in our x right here. We're going to have our x to the fourth all over 4. Of course, when we plug in a 0 minus a 0, all of these terms, of course, are going to wipe out as t goes to 0. Very quickly, I'll leave it to you. You can quickly confirm getting a common denominator of 12. That as you multiply by 6 over 6, here you'd multiply by 4 over 4, here you'd multiply by 3 over 3, you'd get 6 minus an 8 plus 3. That's just going to be a 1x to the fourth all over 12. That's your convolution. Now here's the thing. A convolution, of course, is this integral by definition. But here's the amazing thing. Here's the convolution theorem. If we were to apply a Laplace transform to the convolution, to this integral, mind you, unbelievably, it will be the product of the transform of f of x multiplied to the transform of g of x. So we just have f of s times g of s. Case in point. Here's this convolution, for example 3. Yes, it's an integral, and we could talk about working that integral out. However, what if we were just doing the Laplace transform of such an integral? Well, according to what we're seeing here, this would become the Laplace transform of e to the t, or e to the 1t, multiplied to the Laplace transform of sine of t. And I hope you remember that the Laplace transform of e to the at, as we've been talking about, is 1 over s minus a. So this is going to be 1 over s minus 1. And here, with k equal to 1, we'd get 1 over s squared plus 1 squared. So this is 1 over s minus 1 multiplied to 1 over s squared plus 1. Very likely you would see it all in one denominator. And that is page 1.